last video, we saw that we were not done, that our two methods didn't handle any rational function. We saw that if the denominator had irreducible quadratic factors, then we couldn't factor it completely into linear terms, and method 1 and method 2 didn't tell us what to do with those factors. So we're going to need method 3. What should we do if we have irreducible quadratic factors? Then say let's say I have x squared plus bx plus c. Be irreducible. And let's say that it appears in the decomposition of your denominator. And it even appears a bunch of times. Let x squared plus bx plus c to the m be a factor of q of x. So in the decomposition of q of x, you get x squared plus bx plus c m times. Then in the decomposition of the partial fraction, so in the decomposition of the rational function, you should include so you should include terms with x squared plus bx plus c in the denominator. And you should include them with increasing power until you reach the one that's in your factorization. Now, where this is different than method 2 is with the top. Now, I have a quadratic factor, and so the top is not going to be a constant, it's going to be linear. So 1 degree less than your factor. So here I'll have a1x plus b1. I'll have a2x plus b2. I'll have an x plus bn. Alright, so the top is where the difference is. This is what you should include in the decomposition of p of x over q of x. Let's try an example. So let's say you're asked to integrate this function. Then the first thing I need to do is make sure that my denominator is completely factored. So let's look at this term. My discriminant will be minus 16, which is negative, so it's irreducible. That denominator cannot be factored any further, so I cannot use method 1 and 2. I must use method 3, and I will have these more complicated partial fractions here. I will have one term with x squared plus 4 in the denominator, one term with x minus 2. Now here, I'm told that since my factor is quadratic, the top should be linear, so I'll use ax plus b. Now this one is method 1, I have just x minus 2, I need just simply a constant. Now we need to solve for a, b, and c, so I'm going to multiply this by x squared plus 4x minus 2. I'll get that minus 3x squared plus 3x minus 34 equals ax plus b. Do not forget the parentheses here. All of this will multiply x minus 2. And then I have x squared plus 4 times c. Alright, now I need to solve for a, b, and c. I'll plug in special values of x, but in this case, I like x equals 2, that's my absolute favorite, and then I kind of run out. So let's start with x equals 2. At x equals 2, I'll get minus 3 times 4, so I'll get minus 12, plus 6 minus 34, so I get minus 40. This whole thing will disappear, so I'll get 0 2a plus b times 0, and I get c plus times 8. And so that means c is minus 40 divided by 8. Which is minus 5. Nothing will make this 0. No values of x will make this 0. So the best I can do is plug in x equals 0. Let's see what I get. On the right hand side, I get minus 34. And at x equals 0, I'll get 0a plus b times minus 2 plus c times 4. I'm left with both b and c, but of course we just found what c was, so I can isolate b in this. So I'm going to get that b is minus 34 minus 4c minus 2, so that's going to be 17 plus 2c, that's 17. C is minus 5, so that's minus 10. I'm going to get 7. Now at this point, there is no good value left. So let's try. I have 0, I have 2. Let's not make our lives too hard. I'm going to try x equals 1. I'm sorry I had to erase this, but I have my notes here. So on that side, I get minus 3 times 1 plus 3 times 1 minus 34. So I get minus 34. On the other side, if I plugged in x equals 1, I have x plus b. And then I had x minus 2, so that's minus 1. Plus c, x squared is 1 plus 4. All right, that's what I need. The rest we can do. So I get a, I don't know. B is 7. C is minus 5. And so A will be 34 minus 7 minus 25. That's 9 minus 7, that's 2. All right, so my integral, let me not write it again just so we can finish on this board, is going to be the integral of ax plus b over x squared plus 4 plus the integral of c over, what did we have, over x minus 2. Alright, so the second integral, super easy. We have a formula for it. This one is trickier. It's trickier. We sort of saw these examples in the first video of this series on partial fractions. We saw this type. If I didn't have the 7 there, I would take a substitution. Now, if I only had the 7 there, it'd be like an arctan thing. So the best thing to do here is to split this up. I'm going to split it here at the sum. So I'll have 2x over x squared plus 4 plus 7 over x squared plus 4. And let me actually write it tighter. And the last one we know, so that's no issue. For this one, we said we should use substitution. If I have an x dx, then the substitution x squared plus 4 will work. Du will be 2x dx. That's exactly what I have on top, so this is simple. I'll have 1 over u du, and that part is going to give me log of u, which is log of x squared plus 4. Now for this one, we said this is almost a basic integral with a squared equals 4, so a is 2. So this one will be 7 times the integral of 1 x squared plus 4 dx, and that will give us 1/2 arctan of x over 2. And so we'll get 7/2 arctan of x on 2. Alright, so when you have an integral like this with 2x plus 7 and x squared plus 4, x squared plus any constant, I would split it this way. I'll split it this way so that I can use this substitution on half of it, and I can use the arctan on the other half.